Okay, so hopefully people can hear me now. Good, good, good. Excellent. Well, welcome everyone. I'm not sure which camera we are on. Oh, we're actually on the group camera, so that's good. You don't have to look at me, which is nice. Welcome, I'm Simon Holbeach. I help run Bath Astronomers. If you hear a knock at the door, please shout if you hear anything. That's because I've locked the door outside, so anyone who wants to get in now has to knock gently, because we don't want them wandering around the museum. So thank you for coming. What we'll do is I will start the little screen share, and then we can kick off. It's quite fun doing it back to front. Screen share. And, oh, that's the one I want. Okay. Good. So Chris, you are a co-host. No, you're not. I will just make you a co-host. We've got Roger on the door as well, but if anyone else comes in, if you let them in, that'd be great. Okay. Right, thank you very much. Yes, Bath Astronomers is our monthly gathering. And tonight it's all about just our members' talks. Sorry, just come over here. I'll click that. Hurrah! Woo! I've eventually got it. So, commiserations, the evenings are getting lighter. This time of year, we're very busy with outreach, and all the schools are phoning up to say, oh, I hear you did something in January for this school, or did something in December. Can you do it with us? And say, well, no, because your children have all gone home by the time, and it's too late. So we take a note of them, and then we contact them again come the August time to say, oh, do you want to plan ahead this time? That would be great. But we really do enjoy doing outreach, but it's one of those things that this is the time of year where I start turning schools away, which is a real bit of a shame. So hopefully we'll be able to turn that around by changing, not just offering daytime stuff, but also, sorry, nighttime stuff, but daytime stuff as well. So that'd be kind of cool. We meet up every last Wednesday of each month, excluding the summer. So we allowed ourselves a little bit of a break. And then currently we have 84 people as members, so that's pretty good. We can't all fit in here, as it's getting crowded now. We've actually grown quite significantly over the COVID period. Lots of people taking up hobbies and things like that, or interests that they suddenly found out about. So hopefully we'll sort of work what we're going to do in terms of, as COVID becomes less of an issue and people do start coming, what we'll do regarding venues and things like that. We do have a venue just up the road, which is the Percy Centre, which we haven't been in before. So it might actually be that we move 50 yards up so that we can cater for more people coming in here. We'll still have the occasional bash in here, but if numbers demand that we find a bigger place, then we'll have to find a bigger place. Okay, great. So it's not just me. There are 6 people helping to lead, and indeed Prim was helping me with outreach just the other night, and we all actually met up as our coordination team last week to chat about what we're doing with the money that's coming in and what we're going to do as far as investments and things like that. So what have we got to look forward to? Well, this coming weekend, the star count. Okay, so hopefully people have heard about the star count. It's where you look up at Orion to the south, and from the 26th to the 6th, you find a nice clear night, and you count how many stars you can see in the box that's made up by Betelgeuse, by Bellatrix, by Rigel, and by Saiph. So the 2 shoulders of Orion and the 2 feet of Orion, you count the stars that you can see inside that box. And then you go onto the CPRE's website, just type into Google CPRE star count, it'll bring you the right page. And you, for where your location is, or if you go on holiday during that period or go visiting, you can sort of put a dot in the map of the UK for how many stars you managed to count there. And it's a record of light pollution, and it's done every year. So that's really good to get involved in. Schools are going to be very busy with British Science Week. So loads of things coming in the middle there. We've got the first support that we're doing for the Herschel Museum here. So they'll be on the 13th of March. That's the same day that William Herschel first noted down in his books in 1781 that he saw a fuzzy smudge, which didn't look like a comet. So he was going to have a look at it, and a week later he had a look at it, and it had moved in the sky, and he thought it might be potentially, or whether it was a comet or not, whether it was a planet. Eventually someone did the maths on the orbit and it was definitely a planet. So we're celebrating that. So we'll be helping out with observing in the back garden using, and if we can carry it down, now that we've worked how to take it apart, there's the 7-foot replica telescope up there, which is akin to the one that William used on that night, and he used all the time whilst observing with Carolyn. We'll see if we can get that down into the garden to try and replicate the whole thing. Yeah?
When you say 7 foot, is that the mirror?
The length, yeah, 7 foot upstairs, and I wouldn't want to be underneath it. Yeah, that'd be quite a heavy piece of speculum metal. We've got Mars Day, which sits in the middle of British Science Week. So there's loads of stuff online that's sponsored by SRO. So if you've got a board day, or you just want to do catch up after the 14th, there'll be loads of great stuff going on. If you know any teachers, get them to Google Mars Day. There'll be loads of stuff for the kids to do. On the 19th of March, we've got the Practical Astro Show. If you fancy the 2.5 to nearly 3 hour trawl up to Kettering, this is the first big group of astronomers that are meeting up for 2 years. It's sort of, there's talks, there's demonstrations, there's kit sales, and there's generally chatting to other astronomers. And of course, March is a very popular time because of the where galaxies and things and interesting nebula, for the Messier Marathon, to try and do as many of the 110 Messier objects, see if you can see as many as possible. So typically on the darkest nights in March or very early April is when someone does a Messier Marathon. So perhaps we can try one of those.
Messier.
Charles Messier made a list of all the things in the night sky which weren't comets, because he was regularly scanning the sky a few hundred years ago. And these were annoying because all he was interested in was comets. And if he found a blob, which was actually something that wasn't a comet, he wasn't interested in it. So he made a list of the stuff that he wasn't interested in. So no one knows about him for his comets, but we do know about the list of stuff he mustn't look at in the sky because it isn't going to get him any money. So that's what the Messier Marathon is, to try and spot as many of those annoying blobs to that Frenchman as you possibly can. We'll do some stargazing sessions. So these are ones suggested. So this weekend, it looks like Saturday might be okay. So we would do that perhaps on Saturday the 26th, do a shout for Wello. If you're on the right mailing list or you've joined the brand new WhatsApp group, woo, can't believe I'm advertising WhatsApp. I'm so old, but it's all on the email anyway. So that'll just shout whether it's on, whether it's off. And if you can just RSVP, if you do intend to come along, just so that we know to hold fire. If we're getting cold toes, but we know someone's coming, then we'll stay. But if we're getting cold toes and we don't know anyone's coming, we'll pack the telescopes up. We've got Monkton Combe again, so we'll do a few in there. And we're going to try to do some observing from Alexandra Park. Pick that one because the moon's going to be quite sort of bright. So it's not going to really be too affected by the light pollution of Bath. So we'll see if it's any good. Always try these things.
What time?
There'll be an email note that goes out, but effectively it's about an hour after the sun sets is when they start. So we've been doing lots of outreach, and one of the things we did was the Museum of the Moon with Bath Abbey, and we did that not only just to help and sort of promote ourselves, but also to help them make the best of the exhibition they had in the Abbey. Hopefully lots of people managed to go and see the Museum of the Moon. In return, we suggested they might like to donate something to Bath Astronomers. They've donated £1,000 to us. They knew that we'll be investing in kits to do more outreach. So we had a chat with the coordinating team last week, and we decided to concentrate not only the funds we've already got, but also to look to make requests of trusts and charities that might make an additional donation to make it a bit better. But essentially, we talked about the schools coming in late for the evening stuff. Well, if we can buy a bit more kit, we can run stuff for them after school with the sun up. We can actually do solar observing after school. So that would be a nice offering that we can do. And the other thing we're going to be investigating and pricing up is providing boxes effectively of scientific garb that's going to support Key Stage 1 and Key Stage 2. So you can sort of get, we can give you contacts to get a telescope for the school, and then this will be the supporting stuff that you would use with the telescope. So rather than just get a telescope and go, what do I do with it? We can supply a box of all the fun stuff, the things to try out for the teachers, lesson plans, that kind of thing. So Camilla is very much behind that. I'm very much behind that. So we're going to concentrate on these two activities currently to boost our sort of what we can offer in terms of outreach. And it's fun as well, because when the kit's not there, it being used in schools or for outreach, it's there for us to use as well. So we can have nice summers watching the sun and seeing what it's up to. This coming end of March, we've got Mark McIntyre, who will be talking to us. And this is Mary McIntyre. So you may remember Mary gave a talk to us last year. They're a wonderful married couple, apart from when you mentioned astronomy. They're poles apart. They each want to use the telescope for something. So they're all constantly, well, they're not fighting, but there's a nice tension in, I want the telescope to do this. No, I'm going to do this. So Mark's also part of the UK Meteor Network. He's a computer programmer by trade, but he also helps program, and he's got meteor stations looking up. So he'll be talking about the UK Meteor Network, how to get involved, what the scientific stuff that's useful that comes out of using all this sort of energy, and a little bit of background about himself. So that's our talk in March, okay? But tonight we have our own members chatting about things. And so very kindly, we've got Mike, Roger, Steve, Alice unfortunately said he can't come, Tony, and if time, I'll do the wrap up at the end. I've got a little thing I could do, but if we're running a little bit over time, we'll just leave it to the first four. Okay, so that's the plan. Hopefully you'll learn something for it. If you want to ask any questions, then feel free. I will just whiz up and get Mike's presentation on and then hand over to Mike. So if you just bear with me, I will give you a mic as well, Mike. Mic for Mike. If you want one, there's a mic for Mike. And I'll get your presentation on.
Let's click on it. How's that? Can you hear me?
Hopefully everyone can.
Right. Good evening. I'm Mike Casbon.
Shout next. I'll be your Chris Whitty helper.
Right. This is a little unit I put together for my Dobson-based telescope. You see, as I'm sure you all know, if you've got stepper motors on a Dobson telescope on the altitude and azimuth, you can make it track objects in the sky.
Sorry.
But the problem is you need to calculate the speeds to feed into each motor, which depend on...
I'm not showing your screen, so I'm just going to switch to screen share on. Apologies for everyone. That's the one. There you go. Sorry.
Okay, right. So I put this unit together to control the speed of the motor so that it automatically tracks any object that you want to use. The first row of switches there is where you set your personal latitude. The second set is where you put the azimuth of the object you're observing. Third one is the altitude. A couple of switches on the end there to switch between automatic, off, and manual. So to use it, so you've got your latitude already set. You can find an object with your telescope, read off the figures on the dial, or look on Stellarium, find the object that you want, put the numbers in. And when you press the start button, it'll automatically start putting out a stream of pulses at the right frequencies for it to track the object correctly. You say, this is it running here. This is assuming it's at the North Pole, looking due east at the horizon. And you see after 1 minute, it's shifted around 0.3 of a degree. It should be 0.25, but there's only one decimal place. It's running, this speed here is in sidereals. So it's doing 0 up, and it's doing 1 clockwise. So it's just tracking around 1 revolution in 24 hours. Okay, now the maths to do this is quite complicated. So that's, yeah, next screen, please. And it's when you actually look at what's involved as a whole, it's quite complicated, but you can break it down into a long series of simple steps. So the first thing you do is, this is our star here, little asterisk. We've got our azimuth and altitude readings. There should be a little arc on there, but for some reason PowerPoint didn't import it from the drawing. I don't know why. So we can convert these polar coordinates into an X, Y, and Z, which is straightforward O-level geometry for those of you who did it. Next, please. That's there, is it? Right. Okay, so the next step is we look along the east-west axis, and we look at the Z and the Y coordinates in a plane and convert it back to a polar. We can see here the H, the hypotenuse, it isn't. What I should have said was I've assumed all the celestial objects are fastened to a crystal sphere of radius 1, which makes the maths a lot easier. I mean, you can call it 1 infinity if you like. That's a rather a null concept. Yeah. So as we look down here from the side now, we can see that hypotenuse is foreshortened. It's no longer 1, but we can calculate a new angle, new mag and angle coordinates. Next one, please, Simon. So the next step is to rotate our axes so that the vertical one now lines up with the celestial pole. So that's simply a matter of adding the difference between your latitude and 90 degrees onto the existing angle. So now we've created a new frame of reference. And we can, from that, we can calculate new Z and Y, Z dash and Y dash coordinates. Next, please. The next step is then we look down the new north, new celestial pole axis, that is the one pointing at the pole star, and we can see it as a disk. And we can, so here's our star there. Now we can just create a new, we can find a new, effectively an arbitrary referenced RA angle for our star. We can add the appropriate amount for that to shift it and calculate our new angle, and then we go right back through the maths backwards again, so we get our new altitude and azimuth figures. We can then find the difference between them, work out the speed that we need to actually feed to the motors to do it. I chose an interval of 1 minute, which gives a sort of threepenny bit around the sky with 1,440 sides, which in practice seems to be adequate. You could, I mean, there's 3 microcontrollers in here. There's Arduinos, an Arduino Mega, which is doing all the maths and reading all the switches. And then that feeds out a simple delay figure to a pair of Unos, one of which each one then deals with the azimuth and the altitude. It's done like that, so there's no interruptions in the frequency while it's running. You can do all the complicated maths for the new coordinates, and then quickly transfer it to the oscillator drivers without any sort of glitches. So I chose a figure of 1 minute, so that seems to be enough. I mean, you could do it down to 6 seconds without any problems, but one of the issues is what happens when you go through vertical. The only way a Dobson mount can cope with that is to do a 180-degree shift. So if you had it in 6 seconds, your mount would have to swing round 180 degrees in 6 seconds. Most mounts couldn't do that, and it's obviously potentially dangerous if it's tried. Even in 1 minute, you might find your expensive PC pulled off the table by the camera cable or something. So, but it seems to work. The next one, please, Simon. This is a shot I got of the Orion Nebula with it. You can see it's we've managed to freeze the stars. Unfortunately, where I was, it was extremely windy, So this was the best shot I could get. It's not too bad, but it's not as good as I was hoping for. So I'm quite happy to make any of this code available to anybody who wants to try motorising a Dobson.
So where is that in Orion?
This is Orion Nebula, which is the sort of middle star of his scabbard. He's got his belt there, and he's got 3 stars coming down there. It's the sort of middle. If you look at it with a naked eye, it just looks like a fairly bright star. But if you pair binoculars or something, it soon turns into a smudge. You think, oh, that's not quite something going on there. When you look closely, you've got this rather spectacular nebula going on. But,
Excellent.
anybody else got any other questions?
How long did it take you, Mike?
About 9 months. I had to say it's. I had to sort of run through the process and sort of get so far, and my head would just sort of burst, and I'd have to stop and give it up for a fortnight. Then I'd try again, and I get a little bit further, and in the end, I suddenly realised I'd got there and I'd done it. Then I had to turn around and work it all backwards again.
What's the maths running on? Just a computer?
An Arduino microcontroller, which is basically running a version of C.
They're sort of 15 quid, aren't they?
Yeah, I think the Mega's about 15 quid. The Unos you can get clones for £7.
Yeah.
So you're looking at parts costs of about 30-40 quid.
Yeah.
Cool.
Yeah.
It's better than a rubber band.
Why motorise a dog
Yes, yes.
rather than have some instrument that's designed for imaging?
I didn't quite catch that.
Charles wants to know, why did you motorise a dog rather than...
Well, because I made this telescope in my kitchen in Barbados, and the angle of the horizon there is such that a wedge isn't really practical because it's very nearly vertical.
Yeah.
So the whole thing just gets hideously cumbersome. But yes, it doesn't deal with frame rotation, by the way. So I have actually thought of possibly a way of dealing with the frame rotation if you've got a motorized rotating tube or camera as well. But I think I might not bother. Honestly, for sort of 20-second exposures, it's not really an issue. So stacking software can take care of that problem.
Okay. Thanks so much, Mike. Thank you. Roger, would you like to share the screen and you can dive in as the next person? That would be very good.
Okay.
And then I'll actually ask Mr. Kimmins after you, then we'll go on to Tony. So we're going, yeah, I think that's alphabetical. Yeah, that's kind of alphabetical by surnames. Yeah.
Right.
So hopefully you can share.
Hopefully, just need to get my folder open.
So for the last 2 years, Roger's been giving us a sort of a guide of how his astrophotography has been sort of coming on leaps and bounds. And he hasn't, I don't think you've won any awards yet, Roger. But
Nah, not that good. I have put into the astronomy photographer of the year, but they all got kicked out. But that was 2 years ago, so I didn't even bother last year. So, and I haven't really got anything I feel confident enough with to put in for this year. But there we go, that's it, hey ho. Right, okay, so I'm just going to show some images that I've taken over the last 12 months of some various things. I've got them in little folders on the different things that they are, like planets and galaxies and the moon and the sun and things like that. So I'll just dive in, and if you need to ask me any questions on what I used or how I got them, then just fire away as I go through, if that's okay. All right, so ooh, hang on, wrong folder. Hang on. Right. Okay. Let's do. Right. Okay. So, can you all see that?
someone's been nicking Hubble photos.
Yeah, lovely.
Now, all these images that you'll be seeing are done from my back garden. I live in Sparkford, and I live down a little lane, so I haven't got any street lights. I've got fields down to the south, although I do have some light pollution from Yeovil, which is about another 10 miles away. But apart from that, I'm not too bad, from about sort of northeast to about southwest with a relatively clear horizon. Okay, so this is M81 and M82 in Ursa Major, Bode's galaxy and the Cigar galaxy. And these were done with a 5-inch refractor and an Altair CMOS one-shot color camera. And these were done like about a 1-minute exposure, and there was about 3 hours of these all stacked together. I use a program called Astro Pixel Processor, although some people like to use PixInsight, but I haven't got to that stage, and I find it a bit too daunting when I've already got something that I can just go through the principle of just going, follow the steps 1 to 6, and out comes an image at the other end. I find that they usually come out fairly close to what the final result is, but I just finish them off in Photoshop, or you could use other programs like GIMP or Affinity if you wish. So that's that image.
Roger?
Yes.
Roger, it's a lovely image, it's beautiful. Do you happen to have what you get if you just show the single exposure unimproved version of that?
All right. I'll have a look in a moment later on and see if I can show you, because they're only 1-minute exposures, they are a little bit difficult to see and they look rather flat. Plus the fact, because I'm using a one-shot color camera, the pixel array that makes up each photo sensor is red, green, green, blue. So the overall effect is like a very light green effect over the whole thing, which the program will compensate out of. Okay. If you're a really dedicated astrophotographer, then the way to go is to buy a mono camera. Then you use a red filter, a green filter, a blue filter. And if you want to go into the Hubble space type images that you see and find quite interesting, then you use narrowband filters, which is hydrogen alpha, sulfur, and oxygen. And then you use a combination which the Hubble palette creates from those 3 images into, which isn't a true actual color of the image, but you convert each one. Yeah, you use each one as a red, green, or a blue, although 2 of the filters are towards the red end. So you use one as a green and one as a red. Anyway, I'm digressing a bit. Right. Okay, so we'll just pop over to a closer up view of this one here, just to try and get a bit more detail. You can see some similarities between our Milky Way, where you've got the 2 spiral arms coming around, and you can see some star detail and dark dust matter in the arms as well. This was only done about a month or 2 back, so I'm gradually improving my techniques and integrating lots more pictures to get the detail that I'm now achieving. Although I'm still using the equipment that I bought from the Practical Astronomy show from 3 years ago. So I haven't upgraded my camera or anything just yet. Watch this space. Now this one is one that I took last night. This is a 4-hour exposure on the galaxy known as the Sunflower Galaxy. This is 4 hours, which is 1-minute exposure. So there's about 240 frames all collaborated all together and compressed. Now I started this process about lunchtime, and it finished sticking them all together with a result that you could actually see finally after 4 hours. So, and it was using 126 gigabytes to use to process the images to get the final results. So you need a fairly quick computer and also quite a lot of hard disk space. So be aware on that.
Excuse me, Roger, do you mind if I ask a question?
Yes.
Do you do darks and flats with these images?
Right. Okay. Right. So if you're unaware when you're doing astrophotography, you use these are called the light frames. Then you use dark frames, which is basically the same sensitivity setting and the exposure, but you put the cap on over the telescope. So it's basically correcting any noise that might be in the picture, which will be calculated out. Now you also do what they call flats, which you can either do during the hours of when it's getting bright. You point it up at the sky, put a white t-shirt on, although I use an LED sketch panel, which I just put over the top to get an even balance. If you've got any dust on the sensor or vignetting, it will be able to calculate out the any problems that you would see on the spots and specks of dust on the sensor. And you also do a flat of the darks, so everything's calibrated out. So if there were lots of little dust specks or marks on the sensor, by the time it's all been calculated and you'll get a lovely smooth image, pretty much. So that's the sunflower. You can see some spiral details there, and there's like a dust lane up here, which seems a bit odd, but it's on the edge anyway. Okay, so that's some of the galaxies that I've done. I don't know if many people are interested in the moon. I always seem to be doing pictures of the moon. So at the moment, I'm going through a phase of doing everything with in color, so I can show you the mineral areas of the moon. If you can see that there are some varieties of color on there, if you can see some sort of brown colors, that's the iron in the material that's on the surface, and there are some blue shades around, and that's to do with the titanium, which is also found. So it's quite interesting to see the different makeup of the surface of the moon. So I've got. This was also from this morning, so that's the current phase as it was at about 20 past 2 this morning. So, and these were just done with a 70mm refractor and quite a small 2 megapixel astro camera. So you don't need a huge telescope or anything really big and cumbersome to be able to do anything really good.
These are all stacked, aren't they, Roger?
Those were done with these were done with a 30-minute video, a specific file format called a SER, S-E-R, which is a bit like a Photoshop type format, which keeps lots of detail in it. And you can use a program which is called Auto Stackert, which will be able to stack them all together, and then you can tell how much you want to keep depending on the quality of the image, and then you can just put it back into Photoshop to adjust. Now this one is a much closer up view, which you've got the crater Clavius down here, and that was done with my C11 11-inch Cassegrain, so you can get quite a good resolution. And I calculated I got down to about 2.5 kilometers, measuring some of the small craterlets that were in the Clavius region. So you get some quite good good pictures there. I'll just move over. Mare Imbrium with Copernicus down here, Plato up the top, and then you've got a few Mount Pico, Sea of Crises, and quite a few other details. And just as I was setting up the other day, a plane flew across, and I put it onto Facebook, and a few people found out that this was on its way to the Dominican Republic from somewhere in Eastern Europe. It was a Skyliner, so that was quite interesting. So I thought it was a bird at first because it started almost at the beginning of the sequence. So I managed to extract that as a single image and then just keep it as an interesting frame. Now that's pretty much a full moon, but I've managed to darken it down to get the different color zone, and it's quite interesting to see how it is across the whole surface there. Right, we've just got another region of the moon. Right, we'll go over to some nebula. This is another fairly recent one. This is the Iris Nebula, which I did do about 12 months ago, but I've been practicing my processing techniques to get more of this dark matter and dust blocking out some of the stars to show up a lot more clearly than I have done. And this is my version of the Orion Nebula to what you've seen previously. It's a slightly different process, so it's looking a bit more like something out of Wizard of Oz, but there we go. Everyone likes to process things differently, and this is a different version to what I've normally got, and find that quite interesting. And just a bit further up from the Orion Nebula, we've got the Pleiades, which is quite nice to see. That's about 3 hours of exposure, giving out the various different nebulosity there.
Is that what they call the Seven Sisters?
The Seven Sisters, yes. You can pick out most of it quite easily in a reasonably dark sky with the naked eye, so that's quite interesting. Going back to the Orion Nebula, by the side of the Orion Nebula is this, the Running Man. And I thought I'd just concentrate on that for a change rather than its big famous neighbor. I think you can see the sort of the head and torso and legs and perhaps an arm or two there. So sometimes they can be a bit of a head scratch to work out what it was that they originally thought that it actually was. Right. Okay. So few little planetary pictures. This is obviously Jupiter, and we've got one of the moons here. It's not come out too bad. That's with my big C11 telescope to get the image up to that sort of thing with a small planetary camera. You really need to be able to capture it quite quick because it's 11-hour rotation. You'll get to see how much it moves over even just an hour or two to see how quickly the details move around. And we've got Saturn, and we've got a crescent which was only about the end of January, so it's starting to get more into the last quarter phase like the moon. And that was just with my little telescope as well, so picks out quite well. So, and here we are on the surface of the sun with some sunspots. This was on the back into the 21st of September, when the sun is now starting to pick up again from solar minimum. They're not too bad, but it's not I'm just using the big C11 with a solar filter on the front, which blocks out about 99.9% of the light, and you get quite a good visual look at it. I don't know if you can see this. I've just done a little animation here of partly the part of the rotation, and you can see how the moons move, if you can see that.
Yep.
And this one will be the International Space Station traversing across the, hang on, let's see if I can share, oh, sugar, share screen. Stop share. Hang on, let me try and, oh, sugar, share screen, share screen. Right, let me just, there might be a little dot, I don't know whether you can see it just going across.
There is it.
Yeah, a friend of mine and me went up to White Sheet Hill, which Simon has been up to. There's a special program which will let you know if there's a solar or lunar transit by either the ISS or other satellites. And on this day, on the 4th of February this month, we were treated to the ISS going across, which was very good. We were a bit panicky because there were some very big clouds coming across just as it was starting to get near to time, and it cleared just enough for the transit to be filmed. So we were breathing a sigh of relief there. Much to our, and here is another, that gives you an idea of some of the rotation of, and that was only over a matter of about an hour and a half, just that bit there. So it just gives you an idea of how much we can expect to see during an evening. So there we go. Any questions on any aspects of these photographs that you've seen? I'll stop sharing.
Well, the findings, are they actually close together like that, or are they just looking because they're, you know, have to line up with that shape?
They're reasonably close together, but everything is usually just a line of sight from where we are on the Earth. So they're rough. I think they're roughly in an area close to each other, but not actually all physically tightly bundled together as a group.
Well, they are, aren't they? Isn't there a open cluster dispersing gradually? So they're as close as they look.
Right.
Okay. Well, thanks very much for that, Roger.
Okay.
Excellent. So I will now just prep for Steve's presentation.
There you go. Yeah.
And wait. That one. Click on that. And go back again. Cool. Is that your first slide? Or is that your second slide? That's the one.
There's a request if that light can be turned off from some people. So
Which slide?
that spotlight.
Oh. I'm not sure without plunging everyone into darkness. Where's the workshop ones? Oh, no. So it's this one. That's this one. Did anything happen? No, sorry.
You can leave the slides.
I'll do, yeah.
Yep. Can everybody remote hear me with the microphone?
Yes.
Okay, good. Right, I'm just going to talk on this new fancy state-of-the-art telescope, which I think is probably going to be the future of automated telescopes.
Don't tell Charles that.
Well,
I live a mile from the central, as just Charles actually, about a mile from the centre of Bath, and I've always had a telescope in my back garden. It's just near the bottom of Barfoot Hill, and I've always struggled with light pollution. That's always been a curse for me. And I've done other things to compensate, but I've never really done much deep sky observing. Now, this new telescope has appeared, and it's one of its selling points is it can cut through light pollution, and I'll explain how we use it. And as I've been retired for a couple of years, and my eyesight is really not as good as it once was for looking down eyepieces, this is one reason I've taken the plunge on this. Now, next slide, please, Simon. It is just an f4 Newtonian, not very big. Instead of a secondary mirror, it actually has an imaging chip where the secondary mirror would be. So there's not on the version I've got, I haven't actually got an eyepiece. There is a version which has got an optional eyepiece, but it's actually electronic. You're not really looking at the raw image off the mirror. You're looking at what's coming off the imaging chip. Next slide, Simon. Now, when you switch it on, it generates its own Wi-Fi signal, and you use an app on your smartphone or your iPad or your other Android tablet to connect to it. And it's that is going to be where you're going to see your image from the imaging trip directly onto your tablet or smartphone. So you make the link. Next slide, Simon. You point it up the stars, and next thing you will see, the setup is only about 5 to 10 minutes at most, maybe 5 minutes when you're used to it. You point it up anywhere in the sky where there's a few stars. You press a button. It's got a thing called plate matching, which means it has an onboard map of all the stars. Within about 10 seconds, it will tell you where you're pointing. So you're now ready. Next slide. You're now ready to use its database, which it has a very Messier object, Corber object. It's got quite a high selection of the NGC deep sky objects, planets and comets, and quite a range of stars as well. And if it hasn't got that in its database, you can put in the RA and DEC coordinates and the out as coordinates for the object you want to go looking for. Next slide. Now, before you actually take an image and do anything, you focus. It comes with a Bath mask, which helps you focus. So you point it at a bright star, you focus it, which is the nice symmetrical pattern you get at the bottom right. You also take a dark image, which takes about a minute. That's one of the longest parts of the setup. It takes lots of little images and stacks them into an overall dark image. Next slide. And you're ready to image. Now, one of the reasons why it cuts through light pollution so effectively is what it mostly does. You can have a live view of what you're seeing in the sky, as we've just used in the setup, but you more commonly use a thing called the enhanced vision. And what it does, it takes lots and lots and lots of 4-second images. And this is how it gets around the field rotation as well for an out-as scope. It's stacking them continually using a Raspberry Pi computer, which is built into the telescope, effectively using a deep sky stacker type approach. So 4-second images continue being stacked. It will keep stacking them until you decide you want to stop the exposure. Usually within 20 or 30 seconds, you can see what your object is, whether it's a galaxy, a spiral galaxy, a gaseous nebula, or whatever. Star cluster will come up very quickly, and you can see what you want to see. But more commonly, you often let it run 5, 10, 15, 20 minutes. I've probably done exposures up to an hour for things that when I've wanted to. Because again, one of the advantages, I set it up in my garden, and once I've set down all the system, I can often go inside and sit inside and control it with my tablet or phone inside. So I'm in the warm. So if I'm chatting to my wife and we're doing something, and something I want to take an exposure of for 30 minutes or an hour, I can just let it run, as long as there's no clouds around, stuff like that. So next slide. A side issue, which is quite a nice little selling point, is you can do some real science on it. This startup company in France has teamed up with the SETI Institute, and it encourages you sometimes with a database. It's got asteroid occultations, exoplanet transits, what it calls planetary defense, which means near Earth objects, to point your scope using coordinates it has built in for these events, and you can view them on that. And do some exoplanet or asteroid occultation measurements. So next slide. So it has a database of all the events. I did look at one of these the other night, which was an asteroid covering one of these stars in a particular part of the sky. And it gives you the coordinates, which you can automatically put into your telescope. And it also tells you roughly how long the event's going to take, 4 minutes, 8 minutes, 10 minutes. And you then send that online to the startup company, which sends them on to the SETI Institute. And about 2 to 4 or 6 weeks later, you usually get feedback from SETI saying, yeah, your results have been included in our assessment, and no, you didn't see the transit, but that a null result, as people know in that sort of thing, is as often as good as an actual result. So that's something I've only just started to get into, but a lot of people do seem to find that quite useful, being part of a worldwide community of observers for these phenomena. Next slide. So again, I think that's the one I looked at the other night. So it just went near Bath, so I thought there was a good chance I might actually see a star blink out. And if you stare at the screen, it only lasts about a second or two, and you can't really see it. So I don't yet know whether I saw it because they haven't given me the feedback yet. So next slide. Now let's get on to what I really use it for, imaging. So this goes back to maybe one thing that Charles mentioned. So I've never really seen the Horsehead Nebula. They're just below the line by eye, and I've tried to take the off photograph and never been successful. This is the sort of thing you can get with the scope. The field of view is half a degree. It's the size of a full moon, just slightly under the size of a full moon. This image on the left is the sort of raw image you will get after about 15 minutes of looking at the Horsehead Nebula. You can see it's reasonably well on the screen. You can see it reasonably well. On the right is what you tend to get after a little bit of processing. So all digital images always benefit from processing, just turning up the brightness basically, maybe chopping back on the background light pollution as well, the dark background. But I don't tend to do much more than that. I have got Affinity Photo as a post-processing program, but I don't really use many of its capabilities. I've often found that the image processing capabilities on my iPad's imaging app are just good enough to give me the increase in brightness I need, which is on the right. Next slide. So I'll just zip through. I won't describe all of these in detail, but these are the sort of things you can see very quickly. So that was there is an option where you can get all the data, all the information of what you're looking at and where you are and how long the exposure was. It crops the edge of the image to do that. So that's one option you have. The other images there didn't have that cropped option. You have to try and remember those sort of details. What I tend to do is I tend to take one with the cropped option and then immediately also save the image with the uncropped as well. So at least I've got the information for putting into my file name later on. Anyway, the Eagle Nebula, which was low in the southern sky over the summer, which was one of the first things I looked at. Next slide. Dumbbell Nebula. All of these images, none of these are more than half an hour. Most of these are around 15 to 20 minutes. So I've not put them on here. Next slide. The Crab Nebula, which is currently quite visible up near Taurus. Next slide. Whirlpool Nebula, which is again good to see up near the Plough. Next slide. These were again summer Milky Way constellations, the Trifid Nebula, the Lunar Nebula. Again, about 20-minute exposures, but all of these images I have increased the brightness a bit from what you will see on the screen. But you will see that that's on the screen when you're monitoring it. It's just it needs a bit increasing the brightness. Next slide. M33 Triangulum, which is still around and has been lurking all autumn, and it just fills the field of view. So it's one of the more spectacular spiral galaxies that you can see because you get a good field of view there. Next slide. So again, these are things I've just taken recently. Some Sombrero Galaxy M81, which we've seen in another slide. The combination of M65, 66, M82, Sky Galaxy. All of these are about 15-minute exposures. Next slide. Oh, we keep having a look at the Orion Nebula. So that would be typical of what I would see on my screen after about 10 minutes, because it is a particularly bright nebula. It doesn't really need too much processing. And again, the Flame Nebula near the leftmost star in Orion. Next slide. Now, that's what happens when you take a longer exposure. I think that was about half an hour for the Flame Nebula and a bit of post-processing. There's the Running Man Nebula, which we've had discussed before. Again, the Orion Nebula, slightly longer exposure, a bit of processing. Of course, the main stars in the center, they were heavily overexposed. I haven't done any fancy stuff like masking in a shorter exposure with the triangular trapezium stars. That's the Rosette Nebula, just to the left of I've tried to do mosaics for some of these bigger objects that don't quite fit in, and I'm just about mastering that. I've only had this scope for about 6 months, so I'm still mastering some of these little techniques to get a little bit more out of it. Next slide. It's not really orientated back. The field of view is such that it doesn't really work for planets, and you can't really increase their size. So that's about the best you can get for Saturn. That's an enhanced view of Jupiter. So I've just overexposed Jupiter, but you can see 3 of the moons there. But it's not something I really use it for looking at the planets. Some of the other people online who use these telescopes have tried to use the video approach stack images, but the intrinsic image is always really too small to play around with. You can get the moon. It just about fills the field of view, but again, it's not as good as some of the other images we've seen using other equipment. So it's horses for courses, really. Next slide. Again, another selection. Globular clusters come up within a couple of minutes. There's a nice barred spiral there. Again, a couple of more spiral galaxies. Again, all 15-minute exposures, usually, maybe 20 minutes. Next one. Again, quite low. Again, in my location, I've got a lot of street lighting, and these constellations in sculpture just brush the roofs of the houses opposite me. I wasn't sure I could possibly get that one, but I did. I was quite pleased to see it. M64, which is currently around at the moment in the galaxies appearing in the spring sky. Next slide. And you can get some quite deep sky objects. So there's quite a bright spiral galaxy, 7331 there. But this is Stephan's quintet of galaxies, which Hubble photographs quite spectacularly. And of course, I can't compete with it. It is nice to compare it to the Hubble image, just noting that I am seeing some of the features of those stars, those galaxies, which are colliding with each other about 200 million light years away. So you can see these things, and you would probably have to run this for 20 to 30 minutes to see this sort of detail. Next slide. That's the Stephan's quintet zoomed in. So you see, it's not we're not talking Hubble, but at least we're seeing objects that which are quite deep sky, quite spectacular. And you can sort of say, well, I couldn't see that with the naked eye, but I can actually see it by processing my light polluted back garden in Bath in about 20 minutes. Next slide. Again, M87, which is quite a well-known, boring elliptical galaxy, but you can see the little jet that comes out from the core, which from the supermassive black hole, which was recently imaged in that exercise in about a year ago, I think, using radio telescopes around the world. So that's my contribution to the effort. And the antenna galaxies, which again are colliding galaxies, which again, that's a spectacular Hubble image, but you can just see a hint of what Hubble's seeing with this telescope, again, after about half-hour exposure. Next slide. And that's it. Right, so I'm quite pleased now. I can do deep sky astronomy from my back garden in Bath. So that's basically it.
How did you know the brains of it is a Raspberry Pi?
Oh, they tell you the information.
Do they?
Yeah, it's a startup company in France, which is quite good. There's another startup company, I can't remember what the name is now, France, a French-Italian one, which makes a similar principle scope, but it doesn't look the same. I can't remember what the name is now.
There's a book out on astrophotography projects with Raspberry Pis.
Yeah, it's just a Raspberry Pi. It's got 64 gig on it. It's got a battery built in, and it gives you the Wi-Fi signal. And it's not that complicated, really.
No.
But it's the first one that's appeared in that sort of form, and I can't help feeling that you're going to see a lot more like that in the future.
Yeah.
That do a lot of that donkey work for you.
Sure.
And bypass the eye.
Yeah.
And as I get to my age of my eye, I realise how poor my eye is.
If you're slightly paranoid, you might think that the eyepiece is actually connected to the internet. And you're looking at something.
Well,
you're looking at something.
It's true. You can argue, well, you're not seeing it with a real eye, you can, but you take photography when you go to Venice and Paris and that. I mean, people will take better photographs than you will of those sort of things, but there's still a certain satisfaction that you've seen it in your back garden. Yeah, you're looking at something that okay, Hubble and other people can take it a lot better, but I've managed to do that, and I can go looking for things I want to look at. Yeah. And I find myself increasingly going for these little fuzzy things, which really aren't that spectacular, but I'm just quite impressed that I can see these little fuzzy things.
Can you understand? Can you explain how it extracts the background light? Light pollution.
Well, it's taking lots of 4-second images, so it's not really giving the background light pollution much time to swamp your image, but you're still getting the main image stacked on top of each other for over 15-20 minutes. So there is still light pollution there. It's not completely destroying it, but it's minimizing its effect.
Oh, I see. Okay.
I mean, I do take images where the light pollution is quite noticeable. I get a light corner in the image, and I have to crop that out, which is due for street light. But it minimizes it. But that stacking technique is something that a lot of astronomers, I think, who was the one before me? One of our colleagues. Roger. Yeah. He will take short images and stack them as well. There's a number of reasons you do that, but one is to try and minimize light pollution. The other thing is you don't have to track it that accurately either.
I think the term live stacking is going to occur more and more in the near future.
Yeah, I mean, there's no delay really. I mean, when I'm taking a 5-minute exposure, I'm not waiting over 5 minutes to do the stacking. It is doing it in real time.
Yeah.
You got some questions, yeah? How much is that telescope?
Well, nobody else has asked the other people about their telescopes. We always say that.
It's cheaper than the car, though,
I'm
right?
a keen cyclist as well. The first thing people say, well, how does that bike cost? Well,
Yeah.
but that, you can find out online. That's 2,500, that telescope. And it's a startup company. It hasn't got the advantage, but I'm sure those things will get cheaper with time.
Yeah.
And is it portable?
Very portable. As I say, it's light as anything. I can carry it around, and it's from setting it up to getting those first images on your iPad is, with my practice, it's 5 minutes, but let's say up to 10 minutes, and you're taking images. Then you can go indoors as well if you need to. I sometimes do sit out there with it if I'm taking lots of 10 or 15 minutes. There's no point going inside. I like to see. Sometimes when I'm getting to point at something, I don't realise that there's a tree in the way. So if I'm there, I can know that. If I'm in house and I look, it's all gone fuzzy, then I have to go, oh, bloody tree in the way.
Steve, have you tried something that really benefits from an O3 filter, like the Veil Nebula, for example?
Well, there is in the little cage which holds the imaging chip, there is a C thread, so you can put a C thread adapter in there.
Okay.
1¼ inch filter, and in the past couple of months, I have got a narrowband filter for that reason. I haven't actually found it's that brilliant. It helps. It does increase the contrast, but it's not as spectacular as you might see with a more conventional setup. So I've got it and I've used it on things like the Flame Nebula and Orion and the Veil Nebula. But yeah, I'm not entirely sold on it being a critical part of my setup.
So why doesn't it help in the way it does a visual observer?
Well, it helps, but the light pollution I'm trying to suppress isn't so evident with this particular setup. That's one reason you'd be using a narrowband filter. You'll be letting the H alpha through and cutting out.
Yeah, no, I'm still on the Veil and the O3. I mean, the O3 helps the Veil simply because so much of the the actual light from the Veil Nebula enjoys oxygen, so it's a deal breaker for visual observing. You won't see the Veil at all.
I did show a Veil there, yeah, but I have got I mean, because it's so big, I've imaged it.
Yeah, sure, yeah.
I've got sections, but I have tried it with a filter and without, and yeah, there is an improvement, but it is a bit of a fuff to put the filter in. Actually, I say,
Yeah, sure, yeah.
You've got to, do some gymnastics with your fingers to put it on.
Okay. Thanks so much, Steve.
Okay.
Thank you. And over to Tony.
Right, what I was hoping to do this evening is just to give you an overview of the kind of things variable star observers get up to in their back gardens after dark. Just the equipment, targets, and the kind of charts that we use to present the results. So, equipment, first of all, well, you don't need any. You can observe variable stars with the naked eye. There are many naked eye targets, Algol, obviously, Shelayak, Betelgeuse, and quite a number of others. If you use binoculars, you can increase the number that you can observe quite significantly, and telescopes even more so. And we'll have a look at some examples of what you can see with each of those in a second. The other way to make observations of variable stars is photometrically, using digital sensors, cameras. A DSLR camera is increasingly used by people. I use a DSLR camera. You can use it either with DSLR lenses or attached to a telescope. CCD cameras and CMOS cameras also, but they're generally attached to telescopes, although you can use some of them with camera lenses. So here are my binoculars, the 10 by 50s, the smaller ones, and the larger ones are 15 by 70s. You can see the 15 by 70s I'm used with a stick-like thing called a monopod, and that's really just to hold them steady, because with the magnification of 15, the image tends to wobble about a bit. This is the kind of object you can go for with binoculars. It's a semi-regular variable star called Z Ursa Majoris. If you're not familiar with these kind of charts, this is a light curve. Up the side here, we've got the brightness, so brighter towards the top. Don't be confused by the numbers, which get smaller, but that's the way magnitudes work. And time along the bottom axis here. You can see there's a very clear pattern here. These are observations submitted to the AAVSO database, the American Association of Variable Star Observers, over a period of about a year. The open circles are visual observations, and these observations are contributed by people all around the world. The brown crosses are my observations, and you can see this peaks at around just below naked eye visibility and goes down to just below magnitude 9. So you'd be able to follow most of that in with 10 by 50s, 15 by 70s might be necessary to get to the fainter part of the light curve. So if you use telescopes, you can go fainter still, and you can go after some different targets. These are the two telescopes I use. There's a 16-inch Dobsonian on the right and a 10-inch, the white one on the left. The 16-inch I wheel in and out of the garage. You can see the garage behind there, but I can't move it around the garden very easily. It just stays on this patio, but I can move the 10-inch around the garden so that I can get other targets I can't get with the 16-inch. And with those, you can go after this kind of target. This is a dwarf nova, and you can see it's a binary system. Just excuse me a second. This is a binary system. Consists of a white dwarf, which is the primary star. A white dwarf is the dead core of an old star. It's no longer fusing anything. It's basically a lump of it's a compact object, very compact carbon and a bit of oxygen. And in these systems, it's the primary. The secondary is a red dwarf, and these are quite close together, these stars. They're typically only 100,000, 200,000 miles apart. If you compare that to the diameter of the sun, about 860,000 miles, you can see that these systems would typically fit inside the sun. You can see this stream of material being pulled off the red dwarf here. The gravitational field from the white dwarf is sufficiently strong to draw this material off, and it pulls it off the red dwarf, which for some reason in this picture is coloured blue. It pulls it off, and it hits the accretion disk here in a place called a hotspot, and that's a bright spot that contributes to the light from the system. And if you imagine the red dwarf orbiting in a clockwise direction, you can see as the material leaves the red dwarf and falls into the white dwarf, it's spinning up. So it's preceding the red dwarf as it orbits the main star of the system. The accretion disk here is the material from the red dwarf slowly spiraling around, eventually falling onto the white dwarf. So you have a number of sources of light in this system. You've got the white dwarf, the red dwarf, the hotspot, and the accretion disk. And variability can arise because the red dwarf obscures one or other of these light components, but the main variability happens because the accretion disk fills up with material from the red dwarf and gets hot, and it goes into outbursts, and then it dumps all the material in the disk onto the star, onto the white dwarf, and empties and goes back to quiescence. So that gives rise to a light curve like this. This is a star called SS Cygni. It's one of the most observed of these stars and also the brightest. Again, this is from the AVSO database, all visual observations from 2018. And also these green spots here, these are photometric V-band observations. The brown again are my observations. And you can see that this star has a maximum of around 8, magnitude 8, and a minimum of just below 12. So that's 4 magnitudes. That's a factor of 40 in flux terms. So that means when the star's up here at peak brightness, it's 40 times as bright as it is down here. So that's a big change. And that's why these stars were originally called cataclysmic variables, because people imagined what would happen if the sun suddenly got 40 times brighter from one day to the next. These outbursts here take place about every 40 days or so. And these outbursts are just the disk going into outburst. You can detect the eclipses here, but not visually. You'll need to do those photometrically and with reasonably sized telescopes to do that. So moving on to photometric observations, this is the equipment I use to do that. This is a very simple 4-inch reflector. It's not apochromatic, it's just an achromatic. It's mounted on an EQ5 mount, driven, but not when this picture was taken with GoTo, although I now fitted GoTo to it as well. And the camera on the back here is a DSLR, although I now have a CMOS monochrome cooled camera with a filter wheel for those of you who might be interested in that. And with that equipment, you can take images like this. This is I can't see what the star is actually. Yeah, this is Z Draconis, which is an Aldol type eclipsing binary. And that means that the two components, they're reasonably sized stars, but they're well separated, so they don't distort each other. They remain spherical. And there's a clear beginning and end to the eclipse. So they're a reasonable distance apart, but not so far apart that we can't see them eclipsing. The period of this system is about 1.4 days, and eclipse duration is about 4.5 hours. This observation took place over a little bit less than that, maybe about 3.5 to 4 hours. And although I said it was actually taken, when I think about it, it wasn't actually taken with the DSLR camera, it was with the new CMOS camera. The DSLR would struggle to get down to those magnitudes near the bottom. So this is another type of eclipsing binary. This one is SW Lacerta in the Lizard, for those of you who know that constellation. And this is a different type. It's a W Ursa Majoris type eclipsing binary. And in these systems, the two components, although they're quite large, about sun-sized stars, they're very close together and they orbit in only 7 hours. So if you think about two sun-sized stars spinning around each other in 7 hours, that's a very turbulent system. The eclipse duration here is a lot less. It's probably just about 2.5 hours of observations, I think. And you can see that the curve isn't quite as smooth as the previous one. There are a few little kinks and bends in it. And what's happening in this system is that the turbulence, the high rotation speed, together with a strong magnetic field, generates a lot of star spot activity in the atmosphere of the stars. And so what we see is star spots appearing and disappearing around the limbs of the stars. These stars are so close together, they actually share a common envelope. So they're sometimes called overcontact binaries. And you can think of them as probably a dumbbell-shaped object spinning in space. So as the surface area of the object changes as it spins, you can see when it's edge on, it's at its its dimmest, and then when the two stars are side by side, they're brightest. You can also see here the stars recovering in brightness to peak brightness and then immediately going back into the next eclipse. So with those kind of light curves, you can get fairly accurate timings of the minima, and that allows you to get an accurate timing of the period of the system. This diagram here is called an O minus C diagram, and an observed minus calculated diagram. This one is of another eclipsing binary called AD Andromeda, which is kind of halfway between the two that we've just seen. It's a Shelaic type or EB type eclipsing binary. And if you think about the time of a minimum or time of an eclipse, and you know the period and you assume that the period is constant, you can calculate the times of future eclipses indefinitely out to the future. You can then go and observe those eclipses and compare the times to your calculated times. So up the side here, we've got the differences. This is the observed time less the calculated time for each eclipse. And along the bottom, we've got a scale which isn't actually time, it's the number of cycles, but you can think of that as a proxy for time. So if you look at the 0 line here, if our predictions were correct and all the eclipses were taking place at the predicted times, all these dots would be on that line. And you can see they're very much not. There's quite a good spread either side, really. And the earliest observations in this diagram were 1906. So it's quite a period of time this covers. These observations are stored on a number of databases. This one is the database of the Czech Astronomical Society, and they hold all these observations all the way back to that time. And most of those observations are visual. The black dots, some of them are photographic observations as well. But you can see as time goes on, suddenly things take a much clearer shape. And that's when we started using the digital sensors, digital cameras of various sorts. And the precision and accuracy of the measurements is improved enormously to the point where we see this very distinct sinusoidal pattern in this chart. These red dots, by the way, are my observations taken in the last year or so. And what this sinusoidal pattern indicates is that there's a third component to the system causing the eclipsing pair to wobble back and forth. So as they approach us, the light time, the period that the light path shortens and the eclipses appear to take place earlier. And as it goes away, the light path lengthens and they start to get later. So what we can see here, if my observations are right, is that the system is at its closest approach now, and it's likely to start receding. So this is an image of the Rosette Nebula. It's taken with the telescope, but with the DSLR camera attached to it. It's one of the targets of the HOYS project, which is run by the University of Kent, and the project leader is Dr. Dirk Frobridge. And I think maybe some of you remember him coming to give a talk to the Herschel Society quite recently. The objective of the HOYS project is to target a number of nebulae, which are effectively molecular clouds, because in those objects there are young stars forming, as there are in the Rosette Nebula. And if you can supply images, as this one was supplied to them, broken out into color channels and loaded up to the database. And from that, the computer system can extract hundreds of photometric measurements of stars, including variable stars. So if you keep sending in these measurements, you can track the changes in the light curve and develop light curves for the variable stars in the nebula. Some of those stars are T Tauri type stars, and that's the type of variable star that the sun was before it joined the main sequence and started fusing hydrogen to helium. At that time, 4.5 to 5 billion years ago, it was drawing material out of the molecular cloud from which it was forming into an accretion disk. So this structure's, we've already discussed this structure in relation to dwarf novae, where it was surrounding a white dwarf, the dead core of an old star, if you remember. Here it was surrounding the young sun, drawing its material out of the molecular cloud from which it formed and from which the solar system subsequently was formed, and also, of course, all of us. So I'll put some links at the bottom of that slide for anyone who wants to follow up any of this. I've got my email address there if you want to ask any more questions. Obviously, it's not possible to go into very much detail in a 10 or 15 minute talk, but if you do want to ask any questions now, or if you think of any to ask later, then don't hesitate. Thank you very much.
Thanks, Tony.
Excellent.
Yes, you do.
Can I ask a question?
Yeah, yeah, it's on the latch, so just.
Sorry, I'm struggling to hear.
How did people estimate the brightness by eye? I mean, how on earth did you do
How do you do it by eye?
Yeah.
Yeah, well, if you go into these databases, they have.
I mean, before all this technology was developed.
Sorry.
Before all the technology was developed.
Yeah, well, I do the before the technology stuff as well. So that with the telescopes, you can draw off a star chart, and on that star chart are predetermined magnitudes of the stars surrounding the target. So you can then compare the brightness of the star that you're trying to estimate the brightness of to standard magnitudes. If you saying how did people estimate brightnesses before, you could actually measure them. There's a degree of estimation involved in all those things, really. I think the most accurate measurements in days gone by were using photography and photographic plates. Obviously, there's a chemical reaction taking place there, and that would be related to the amount of light that was striking the plate or the photographic medium. And digital cameras are doing the same thing now, but just more accurately. So a pixel just records a charge which is proportional to the amount of light that's fallen on it.
Right. Okay. Thank you.
Excellent. Any other questions? No? Well, thank you very much, Tony. Excellent.
Let's stop sharing.
Whoa, it's quite dark in here. Okay, it looks like we're in some police cam that's looking at shoplifters. So don't nick anything. We're in the museum. Things are valuable, but don't nick anything, please. Right, so we're actually up to 9 o'clock. So I suggest we skip my last one and we say our goodbyes now, rather than sort of me droning on for another 10, 15 minutes. You probably won't like. Come to one of our observing events and I'll drone on to you for hours on end. So don't worry about that. And I can always fit in my little slideshow in another event. So that's great. I hope you enjoyed it. Yep. But the idea is sort of, it's not just about getting professional speakers in or professional scientists or whatever. It's getting sort of ordinary people actually just doing the hobby and enjoying it. And you can hear it in their voices. If you're crazy enough to build your own telescope, we're going to call you Mike. If you're just going to buy one that does it all for you, I'm going to call you Steve. And if you've got lots of red wine, I'm going to call you Charles. But it also can show you with a bit of dedication and not breaking the bank too much, what Roger's achieved in the last 3 years since he bought that kit at the Practical Astronomical Show. And he's actually going back on March the 19th. So hopefully his good lady's going to stop him taking his credit cards. Otherwise, it's going to be the next 3 years that he's going to do some amazing work. But that's just a show of dedication. But you've seen the love in all of the voices that you've heard tonight, and that's what we're trying to inspire. So thank you very much. If you've got any questions, please don't hesitate to ask me. You can either do it now, you hang around, or you can do it in any of the other events that we've got. So our next meeting is on the 30th of March. But I've got to say the observing evening looks like Wello's a possibility this weekend on Saturday. So that'd be great. And if you're really bored, you can find Charles and me at the top of Bath Abbey on Friday night. Oh no, is what night? Actually, which night is it? It's Saturday night, isn't it, Charles? You're at the meeting. Is it Friday?
Yeah.
Oh, it's Friday. Okay, so it's Friday. Oh,
I'm coming on Friday, Simon.
so no, you're right. You are right. It's Friday night. We're up there. Wello is going to be Saturday. Yeah, so, okay, right. Excellent. So thanks very much. And thank you for coming. And I hope to see you very soon. Thanks.
Bye.